Hey guys, we are going to cover our third section of chapter 3. This one we cover the hydrosphere and the biosphere. We covered first the geosphere with the core mantle and crust. Then we covered the atmosphere with the stratosphere, the troposphere, all the different layers of the atmosphere. And now we're going to do the other two. There's 4 spheres: geosphere, atmosphere, hydrosphere, and biosphere. We're covering the last 2 together in one section. All right. So let's see what we have. The word hydro means water, so it is all of the water at or near the Earth's surface, meaning on the surface or floating in the atmosphere like clouds and such, or buried deep in the ground. Any water at or near the surface. Oceans, lakes, rivers, wetlands, polar ice caps, stuck in the soil, like I said, and then, hang on, let me get a thing. Stuck in the soil, okay, rock layers, beneath the surface, up in the clouds, all of those things together, that's all the hydrosphere. No matter where you find it on Earth, if it's water, it's hydrosphere. The water cycle is how it gets moved around. Let me see. Make sure I don't erase the screen. There we go. All right, so the water cycle is that you've learned in many, many years in the past, it's that continuous movement of water from the ocean to the atmosphere and back. And usually it's ocean. It's not only ocean. It can be the puddles in your backyard. It can be laundry hanging on the line. It doesn't have to come straight from the ocean, but that's where it does most of the time. Most of the evaporation is coming off the oceans. It goes up into the atmosphere, condenses into clouds, and comes back down. So evaporation is the first step. It's the change of the substance from a liquid to a gas, and you've learned that before. You can see the word vapor in there. Vapor is another word for gas. So evaporation is the changing of a substance from a liquid to a gas, and the water is continually evaporating from the oceans, lakes, streams, soil, okay, puddles, your laundry line, all of that stuff. But the majority of it gets from the ocean. Let's see. So if evaporation is the first step, let me see if there's another line. Yeah, if evaporation is the first step where it goes up, condensation is the second step. That's where it changes from a gas back into a liquid, but that starts as water droplets up in the clouds. The clouds cannot form unless they have dust particles first. Bill Nye does a really cool experiment where he has this great big jug and he tries to set up condensation in it, and it doesn't work. But then he lights a match, blows it out, and drops it in there, and then does it again. It works because then the water droplets can condense on the smoke particles. The water has to have something to condense on to get it started. Okay, so what happens when you're making clouds is that it will condense around dust particles high up in the atmosphere, and then the clouds up in the clouds, the droplets are going to crash together and get bigger and bigger and bigger as they go, and heavier and heavier and heavier, and then finally they're going to fall. Okay, rain, you already know that the fancy word for rain is precipitation. And it's not just rain though. It can be rain, snow, sleet, or hail. Anything that's fallen from, any water that falls from the sky, okay, is precipitation. The word precipitation actually means to fall. Like if you were being fancy, even a person falling off a cliff would be precipitation. But it just means fall. We use it for weather. Okay, clouds, rain, snow, sleet, and hail. So we've got evaporation, condensation, precipitation. All right, let's see what happens next. Okay, evaporation, condensation, precipitation. Those are the 3 main steps. It's a real easy one to follow. Most of you guys have learned it in the past. Evaporation coming up off the oceans. Let me find another color. Evaporation coming up off the oceans, okay, where you see the word vapor, you turn the liquid into a gas. Condensation is where you put it back into a liquid again, but it spends a lot of time up here in the clouds until it gets good and heavy. When it gets good and heavy, then it'll drop, and when we drop, we say precipitation. Precipitation actually means to fall. All right, so we're going to talk about the Earth's oceans, and we're actually going to cover the Atlantic Ocean, the Pacific Ocean, the Indian Ocean. But technically in real life world, when you're thinking of ecology and environmental science and protecting the world, there is only one ocean. All right, because it's all connected. If you look here, let me get my pencil back. if you look here, this is the Pacific Ocean, okay? It's connected down here at the bottom. This is the Southern Ocean around Antarctica. It's connected to the Atlantic, and this is connected to the Arctic Ocean. And swinging back around here, this is the other side of the Pacific over here, and it's connected to the Indian Ocean, which is also connected to the Southern Ocean. That is one ocean, okay? Even up in here, the Gulf of Mexico, okay? Right? No, that's not the Gulf of Mexico, but that's up around New York, okay? The Gulf of Mexico is here. All right, so all of these, it's just one ocean, okay? And what we do in one is going to affect all the rest. That's another thing that we have to be careful about when we're talking about ecology and environmental science and protecting the oceans and protecting the climate, because we learned that what happens in, like I said, we know what happens in one part of the one sphere of the earth is going to affect all the other spheres. And so all of the oceans are joined in one single large body called the world ocean. Okay, that's what they call it, the world ocean, when you want to say that it's connected. And the oceans play a very important role in the regulation of the Earth's planet's environment. And so we've talked about this in the past, how important it is. We learned about the atmosphere in this chapter. Okay, we talked about how the carbon that we're adding to the atmosphere is heating it up with the greenhouse effect, right? We talked about that in section 2, the greenhouse effect. It is adding to climate change because what's happening is as we heat up the atmosphere, the oceans are heating up. And once the oceans are heating up, more and more of the ice is melting, which is increasing the problems of heating it up. Once the oceans warm up, the oceans have such a big part of regulating the climate, okay? Regulation of the planet's environment. They regulate the climate. And when we start heating up the oceans, we start messing up the climate really, really badly. Okay, now again, there is only one ocean, but we usually talk about them in specifics. The Pacific Ocean is the largest of all the oceans. Okay, I'm not going to have you memorize the specific size that it is, but the Pacific is the largest. It also has the deepest point in the ocean floor. It's called Challenger Deep. The deepest part of anywhere in the ocean is in the Pacific, and that space is called Challenger Deep. Challenger Deep is located near the Philippine Islands, okay, at the bottom of the Mariana Trench. So Mariana Trench is near the Philippines. And inside the Marianas Trench, you have the deepest part of the Pacific Ocean, and that is called Challenger Deep. It is so deep. You know the tallest mountain is Mount Everest? You could drop Mount Everest into Challenger Deep, and you would still have a whole bunch of space up here on top. Okay? There's no mountain in there. They pretended to drop Mount Everest down into Challenger Deep, and there's still a whole bunch of space on top. Okay, so Challenger Deep is way, way bigger than Mount Everest. It is tall. Okay, that's going to be important, how deep the Challenger Deep is, and that it's found in the Mariana Trench near the Philippines. Okay, and that is part of the Pacific Ocean. That's 5 or 6 things to put together there. All right, now also with the Earth's ocean, oceanographers divide the Pacific into North Pacific and South Pacific. This is the Pacific here. Okay, we divide it into North Pacific and South Pacific because the equator cuts right through the middle of there. Okay, so we have the North Pacific and the South Pacific. Now the currents in the ocean, they flow clockwise. Let me find another color. I guess white? No, not white. Maybe this bright yellow, we can see it. They flow clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. And that has to do with the spin of the earth. Your toilet does the same thing. Draining down a toilet in the tub. It does the same thing because of the spin of the earth. In the northern hemisphere, it goes clockwise. All right, in the southern hemisphere, like Australia and parts of South America, goes counterclockwise. And that has to do with the spin of the earth. It has a fancy name called the Coriolis effect. All right, the second largest ocean is the Atlantic. Okay, that's the one over here. This is where New York and South Carolina, they both have ocean front. That's the Atlantic. All right, and over here on this side near the Amazon in Brazil. Okay, this is the Atlantic. All right, it's the second largest. It's only about half the size of the Pacific. Okay, so even though we look at the Atlantic, it looks like there's a lot going on here. It's only half the size of the Pacific. We do divide this in North and South also. All right, we divide that into North Pacific and North Atlantic and South Atlantic, Southern Atlantic. And it's going to have the same thing happening where it's the currents flow clockwise up here and counterclockwise down here. Let's see, the Indian Ocean is third. And then the Arctic is the smallest. Arctic is the one up here in the north. Indian Ocean is right here. Okay, this is the Indian Ocean. Do you see Australia? This is Africa. Okay, and this is India. Okay, so that's the third largest. The Arctic Ocean up here in up near Sweden. You remember Frozen? Up near Sweden and Finland, Northern Europe, Greenland, Iceland. That's the Arctic Ocean. It's the smallest. Most of it's covered up in pack ice, okay, floating ice, and winds and waves drive this frozen seawater together and puts it together in a large mass, so it's called pack ice. Now the trouble is, as we said, with climate change, the pack ice is becoming there's less of it in the winter, and it thaws faster in the summertime. So the pack ice we're having trouble with that, and the pack ice is actually very important to help regulate the climate. Not to mention for polar bears to hunt. Polar bears can't hunt without the ice, but it's not just polar bears, it's a lot about the climate as well. Now, again, with this section of the thing is the hydrosphere, so it's all about water. Okay, the ocean water is the main thing we talk about because the ocean water is the difference is the salt water. You know that ocean is salt water and freshwater is less salty. Now, it's not that there's no salt. It's not that there is no salt in freshwater, it's just so much less. But the oceans, they're just covered in it. And when we talk about how much salt there is, we say the word salinity. Salinity is the measure of the amount of salt. So the oceans have a high salinity and the freshwater has a very low salinity. Okay, so salinity means how much salt there is. Okay, how much dissolved salts in the amount of that liquid. Okay, so salinity, though, in different parts of the ocean, if you get a lot of rain or during the monsoon season when it does rain a lot, there's going to be less salinity in that part of the ocean. Okay, and so salinity is lower in places that get a lot of rain or places where fresh water flows into the sea. So the ocean isn't steady amount of salinity everywhere. It varies. Okay, and especially like if you're like I said, if you're part of the equatorial regions, when people who get monsoon seasons, you've heard of monsoon, that rain comes down basically fresh water, and so it changes the salinities of the ocean a little bit, and especially where a big giant river flows into the ocean, that area, it's like an estuary is what they call it. That estuary part where the river is flowing into the ocean is going to be less salty than the rest of it. And the salinity is higher in areas where the water evaporates fast and leaves the salts behind. Okay, so if the water is steady evaporating really fast, it's going to be saltier underneath because only water goes up, the salt doesn't go up. So not all of the ocean has the same salinity throughout. Okay, try to pay attention to when it would be lower and when it would be higher, because this is what we talked about right here on this screen. Okay, it'd be lower in places and higher in other places. Now, the salt that's in the ocean, most of it is sodium chloride. Okay, sodium chloride is the majority of the salt, and that's exactly the same salt that's on French fries. Okay, sodium chloride. However, any of you guys have been to the ocean know that that does not taste like French fry salt. That does not taste like table salt. If you've been to the ocean and you've accidentally gotten some in your mouth, it does not taste like table salt. And that's because it has so many of these other things in it. Okay, there's potassium and calcium and sulfur and magnesium. None of those things are in table salt. Okay, potassium, calcium, sulfur, magnesium. And that's what makes it taste different. Okay, but the majority is the same stuff that's in table salt. Okay, sodium chloride. but there's so much more, and that changes the taste. But don't drink it. It'll make you sick if you drink too much. But I know that when you do go swimming, it gets in your mouth sometimes. It just does. Just don't drink too much. All right, now when we're talking about the ocean, let's talk about not just the salinity of the ocean, the temperature of the ocean. All right, the surface of the ocean up here is warmed by the sun, okay? While the depths of the ocean where sunlight never gets are very, very cold, just above freezing, okay? All right, so the surface waters get stirred up by the waves and the currents, okay? So that the warm water will mix slightly, okay, with this next layer. Okay, so the surface zone might be as much as 350 meters deep. This doesn't have any numbers to tell you how deep this is. All right, but it might be as much as 350, this warm weather, depending on how much gets stirred up by the waves and the currents that mixes up this warm level. But then below that is this thermocline. That's this light blue layer. Okay, this thermocline is a layer that's about 300 to 700 meters deep, and the temperature drops steady. So yes, it gets colder the deeper you get up here. Okay, it gets colder when you get deeper, but when you hit this one, it's like almost an instant drop through that dish. That gets cold really, really fast. And then as you get down here in the deep, you know, yes, it's going to stay cold, but by this time you're pretty much just as cold as you're going to get. It doesn't get that much colder because by then it would be frozen and it's not going to freeze. So like here would be like 30, 32 degrees right here, just enough to make it so it doesn't freeze. Here's another version of it. The surface zone up here is the warm upper layer. Okay, sunlight can get here, so since sunlight can reach this layer, this is where any photosynthesis that's happening in the ocean would be happening, up here in the surface zone. The current mixes when the wind blows. This gets mixed around, okay, bringing the cooler water up and the warmer water down, so that this is pretty warm. Now when you get down here, this is about 300 to 700 meters, okay. This zone, the temperature drops much faster when you go further down. Okay, and the deep zone here, okay, extends down to the base, from the base of the thermocline down to the bottom of the ocean, and it averages about 2 degrees Celsius, which is between 31, 32 degrees. Okay. All right. Now, again, we said a minute ago that the ocean is going to be a global temperature regulator. Okay. Do I have another click? Yeah. Okay. All right. So one of the most important functions as far as protecting the earth that the ocean does is the fact that it absorbs and stores energy from sunlight. Okay, it takes that heat energy and holds it so that it can regulate the temperatures around the earth, and it absorbs the heat and it's going to release it slowly. Okay, it's going to absorb the sun's heat and release it slowly, so that if you have an ocean current that's going beside somewhere that's really, really cold on land, but the ocean current has been, you know, it was down by the equator and it's moving up the side of the Atlantic. Think about this. Okay, we don't have a map. Let me see. All right, this is going to be a rough looking map, guys. Okay, here's New York and Carolina, and down here is Florida, okay, and Texas, and then getting down here into South America. Okay, you guys kind of see what I've got going on here? This is the Atlantic Ocean. Okay, so the Atlantic Ocean is sitting here kind of warm. All right, steadily absorbing sunlight, okay, getting warm. I mean, it's still water, but it holds the sunlight, and then it carries that heat as it goes up. So around here, this is where Iceland and Greenland would be, and then England is over here. All right, it carries heat to these places that would be too cold otherwise. So the ocean actually helps to regulate the temperatures in these areas. It absorbs the heat and releases it slowly to land, and therefore the temperature of the atmosphere will change slowly. Okay, that'll help keep this regulated. And if the ocean didn't regulate the atmosphere and surface temperatures, they would be too extreme for life to exist on Earth. It would be way too cold up here. All right, and it actually helps to cool the places down here that would be way too warm. So the ocean helps to balance things out. Okay, so that's one of the main things. It's a global temperature regulator. Helps to balance out the heat. The cold places don't get too cold and the hot places don't get too hot because of what the ocean can do holding the sun's heat. All right, here's another way that it shows not just globally, but in local areas. Okay, the local temperatures are also affected. Like if you live right near the ocean, first off, the ocean is going to change the temperature of the whole world. That's what I was just saying a second ago. Now we can think about just the individual places around the world, okay, are also regulated by the world ocean. As the currents circulate the warm water, they flow past climates. They're going to make the climates more moderate. So here we have the cool morning air, and this is warm, okay, and this will help too. The large bodies of water have a moderating effect on the atmospheric temperature and can affect the climate near the region. A large surface water can keep the region from experiencing temperatures in the summer, too high of temperatures in the summer and too low of temperatures in the winter. That's what I was talking about, the balancing effect that the ocean has. And so a lot of places that are near the ocean can take advantage of that. The currents of the ocean. Okay, let's see. All right, so they're like a stream. Do you remember when you watched Finding Nemo and Nemo went swimming with the turtles in that area where the current went really, really fast, and then they had to go out of it and get in it, go in and out of it? That is what I'm talking about here. These are the ocean currents. Okay, now they're driven. The ones at or near the surface, these red ones, are the surface currents, but they also have these blue ones that are near the bottom of the ocean. They travel along the bottom. Okay, so the ones near the top are called surface currents, and the ones at the bottom are called deep currents. The surface currents are driven by the wind. The wind is what makes them blow, and it's a result of the global wind patterns. I showed you that in the atmosphere, that in certain parts of the globe you can count on the wind blowing the same way all the time. We do that here. Think about global winds. When we are looking for snow, when we're looking for a snow day, you watch the weatherman on TV, you look to Arkansas, don't you? The weather always moves from Arkansas towards us. Okay? Think about it the next time you watch the weather and you're looking for a snow day. The weather always blows from Arkansas towards us. Okay, that's because of the global winds. And it's not just happening here, it happens everywhere where there's a particular way that you can expect the wind to blow most of the time. And because of that, it also works on top of the oceans to set up the ocean currents. Okay, now the surface currents can be warm or cold. They can be warm or cold, but they don't often mix with one another. The different temperatures don't often mix with one another. And here's some more of our ocean currents. Again, we have clockwise up here in the northern hemisphere, counterclockwise in the southern hemisphere. All right, and these are the different major wind currents. These are what the sailors relied on when they were trying to travel. Like right here, let me see, let's find another color. This is America, this is USA right here. And so when they were traveling from here to England, they had a current to help carry them. But if they were traveling back from England to us, they didn't have a current, so it was harder unless they circled all the way around. That's how Columbus got here. He circled all the way around. He followed the currents. Okay, these currents are just set up. Now, another problem, this is what we're talking about, is we change the temperatures of the ocean. These currents are getting messed up. All right, and it's going to create all sorts of havoc. The deep ocean, the deep currents, these are the ones that I said were way on the bottom of the ocean. They're stream-like movements also, but they travel very, very slowly along the ocean floor. The deep currents form when the cold, dense water from the poles sinks below the warmer, less dense water near the equator. So think about it. At the equator, the water is going to be warmer. At the poles, the water is going to be colder. So the stuff at the poles sinks down and goes under down at the bottom. The warmer currents are floating nearer to the surface. The densest and the coldest water, of course, is off the coast of Antarctica, and it flows very, very slowly northward, producing a deep current called the Antarctic bottom water. Okay, so these are, if you think about it, because these currents are flowing along the bottom of the ocean, anything that dies and decays, that body parts and that nutrients that used to be in that body, that animal, whatever it is that happens to die, is going to sink and filter down to the bottom of the ocean. Those deep currents will take those nutrients and push them along with them and eventually bring them back up so that the higher up levels of the food chain can get the nutrients back again. So it's one thing that the deep currents do for us. They kind of scratch the bottom of the ocean to bring those nutrients back up to everybody else. Now we'll talk about freshwater. Okay, we talked about that was all a whole bunch of stuff about saltwater. All right, freshwater is water that contains insignificant amounts of salt. Like I told you, it's not that there's no salt. It's just that there's tiny, tiny amounts of it. Most of the freshwater on Earth is locked up in the ice caps and glaciers. Okay, at least as long as we still have glaciers. All right, while the rest of it is found in places like lakes and rivers, wetlands like swamps, in the soil, and up in the atmosphere. A river system, like we have the Mississippi River system here. This may not be the Mississippi, but it's a good idea. Is a network of system that drains an area of land and contains all the land drained by the river. So all of this land is part of the river system. Okay, it has its source up here. You know, the source of the Mississippi is up near Missouri somewhere. Okay, I believe. I may need y'all's help with that. I believe it's up in Missouri. All right, and then it comes down here. We have our delta. Okay, this is where we live here. Well, this is Louisiana. All right, we're close to here. But all of these, I've scribbled over top of it now, but all of these small rivers that join in right here are called tributaries. Okay, these small rivers that join into the big river on the way down. Tributaries, and that's one thing you'll need to know too. So you got the river source and the tributaries that build in. Okay, this is the floodplain down here. Like we live in the Mississippi's floodplain. And then down here you have the delta. All right, so let's see what we have. The river system is a network that contains all of the land drained by the river, including the main river, the smaller streams, and the largest ones, and the tributaries. Okay, so all of this is included in the river system. Groundwater is just exactly what it sounds like. It's water in the ground. Okay, but there's a little bit more to it than just that. Okay, as it rains or snows or anything like that, the precipitation comes down here and starts to sink into the ground and run off. It'll either run off on top of the land down into streams and eventually down to the river, or it will sink down in to the ground. All right, when it sinks down in, then it sinks down, it trickles down through the ground, and it collects this groundwater. And although this makes up only 1% of all the water on Earth, this is not a lot of water. Okay, this is only 1% of all the water on Earth, but this is what we use to fill all of the human needs. All of the human needs we fill with groundwater. All right, that's our fresh drinking water, our agricultural water for like farms and such, industrial water. This is everything. Everything we use comes from the groundwater right here. When it goes down on the last slide, when that water sinks down and it collects in what's called an aquifer. Okay, these blue areas here are the aquifers. Okay, and that's where a storage area underground, it can be either a cave underground or just holes in the rock. But what we do is we can tap it with a well, and then we can pull it up that way. Okay, so an aquifer is like a storage place for groundwater. It can be a cave or something like that, but sometimes it's just spaces between the rocks. Okay, it's not really an actual place that you could like jump in there and go swimming. It's not really like that. Sometimes it's just spaces between the rocks. Aquifer is a storage place for groundwater. All right, moving on. We're done with the hydrosphere. Now let's move to the biosphere. Bio means life. All right. So what we have here is there one more click? Yes, okay. The biosphere is the part of Earth where life exists. And it's only about 7 miles down into the ocean and then 6 miles up into the atmosphere. And that's it. That's all we got. Okay. And within it, the material that the organisms require to live has to be continually recycled within this area. Gravity is actually going to do most of the work for us. Gravity, you know, again, talking about nutrients, right? Because however much calcium our body needs, however much carbon, however much phosphorus and potassium, however much water, whatever we need for our bodies and every other organism on the earth, there's only a certain amount. Remember, we learned about spaceship Earth, right? We can't go get more calcium somewhere. We can't just go stop at the asteroid belt to pick up more nitrogen. All we have on Earth is all we have. And so we have to recycle these nutrients so that one generation can use it and then the next generation can use it. You know that when an organism dies, the worms and the decomposers and stuff will break that down, and then the nutrients are available for the next generation to come through. Gravity actually helps with a lot of that cycling. Okay, it helps to allow a planet to maintain the atmosphere, and it also helps to allow the planet to cycle those materials like I was talking about. So we have to have suitable combinations for the organisms to survive, and those suitable combinations of characteristics of temperature, of the suitable conditions, are only found within the biosphere. Okay, wherever an organism lives, that means it's part of the biosphere. So the suitable combinations that an organism needs to survive are found only in the biosphere. Let's see, is there one more click? Yeah. All right, so the biosphere is near the Earth's surface, okay, because most of the sunlight is near the surface. All right, because you know that plants are the starters of almost every food chain, right? And plants need the sunlight. So the biosphere is located near the surface because the sunlight is near the surface. The plants need this sunlight to produce their food, and almost every other organism is going to get its food from the plants or algae. And the algae that's floating on the surface of the ocean is called phytoplankton. Okay, phyto comes from the same thing as photosynthesis. Okay, phytoplankton, those are little algae that will do photosynthesis floating on the top, and then other algae called zooplankton will eat them. Okay, zooplankton for animal, phytoplankton for plant. Okay, alrighty. Now, as we're moving energy through the biosphere, okay, the energy is used, is there another click? Yeah. The energy used by the organisms has to be obtained in the biosphere, and it has to be constantly supplied for life to continue. Remember, I said it's a circle. All right, so the ecosystem is sustained by a combination of one-way flow of energy and cycling of nutrients. When something dies, it gives its nutrients back. Okay. When an organism dies, the body is broken down and the nutrients become available to other organisms. This flow of energy allows Earth to continue to exist. So it does sound creepy to be eating dead things, but that's exactly what's happening, except that it's not dead things anymore. The decomposers break down the nutrients, and then the plants use those nutrients to start the next cycle. All right, so remember when we talked about spaceship Earth, we talked about closed system versus open system. The nutrients that the biosphere needs, the carbon, the phosphorus, the potassium, that's all, this is all we have. Sorry. So the Earth is considered a closed system for matter and nutrients. We can't just go to the asteroid belt and pick up more carbon. This is all we got. So the Earth is a closed system for matter and nutrients, but it's an open system for energy. Remember that you can get more sunlight in as much as you need it, and most of the time we can get plenty of the heat out. Okay, except we're messing up the atmosphere, but we still get a lot of heat allowed out. Not enough, but we're getting there. All right, so when we talk about these systems, let me get this yellow. Okay, so closed systems are systems that cannot exchange matter or energy with the surrounding. See this terrarium? Okay, you can't get anything out, can't add anything back in. The only thing you can add is light. Okay, the light energy is the only thing that can come in. The open systems are systems that can exchange matter and energy, and that's not going to work. We can only exchange energy. Now today the Earth is essentially a closed system with respect to matter, but an open system for energy, as the energy can travel from plant to animal, which is eaten by the other animals, and then the heat that's produced can escape back out. Okay, that's right here. The lost is heat. And that, I think, is the end of our notes. All right, so this again covered, so this is the last of the 4 spheres. We covered the geosphere, the atmosphere, and now the hydrosphere and the biosphere. And technically in this terrarium you can see all 4 spheres. All right, you have the geosphere, this is the Earth, the hydrosphere, this is the water, the biosphere, okay, the living parts, and the atmosphere. So this little terrarium has all 4 parts of the Earth's spheres put together for you. I'll see you the next time, guys. Bye-bye.